तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last class we were discussing about coagulation and flocculation, and we have seen that what is the necessity of this coagulation and flocculation, and by going for or by adding coagulants how can we remove the turbidity. Today we will discuss about the next treatment unit, that is softening. And softening is usually used for groundwater because most of the time surface water will be having hardness within the permissible limit, and we have discussed in detail about hardness when we were discussing about the water and wastewater characteristics. For drinking purpose, a hardness up to 150 milligram per liter as calcium carbonate is acceptable. If the water is having high hardness, it is known as a hard water, and if the hardness is low, then it is known as soft water. And we have already discussed what is this hardness. Hardness is nothing but the presence of polyvalent metal ions in the water, but not all polyvalent metal ions are considered in measuring hardness. Usually we take the presence of calcium and magnesium in water as hardness, and hardness we can divide it into different categories: carbonate hardness, non-carbonate hardness, calcium hardness, magnesium hardness, or temporary hardness and permanent hardness. We have already seen this one in detail, but I will just mention what each one of them represent. Carbonate hardness is nothing but the hardness which is equivalent to alkalinity. So that is known as carbonate hardness, and non-carbonate hardness is the one which is in excess of alkalinity, or the ions like calcium and magnesium present in the form of sulphate, nitrate, chloride, etc. Then it is known as non-carbonate hardness. And coming to temporary hardness, the hardness which can be removed by boiling, that is known as temporary hardness. That means the temporary hardness is equivalent to carbonate hardness, and permanent hardness is the one which cannot remove by mere boiling. We have to add some extra chemical for the removal, that is known as permanent hardness. And calcium hardness is nothing but the hardness caused by calcium ions, that is calcium hardness. And magnesium hardness is the one which is caused by magnesium ions. Why we are not considering the presence of monovalent metal ions for hardness? The reason is, if we add salt to the solution, the salt formed by the reaction of this monovalent metal ions and salt, they are soluble form. So usually we won't consider them for the hardness determination or as hardness causing elements. So what is the disadvantages of hard water? The most important one is, if hard water is there, the soap consumption is very high. Okay? If the water is hard, the lather formation is very difficult with low quantity of soap. Another one is, it creates or it forms scale on all heat exchangers and boilers. So in industrial purpose, hard water is not recommended, because if it is used in the boiler, it will be forming thick scale and the heat exchanging capacity will be reduced drastically. So for industrial purpose, we need almost zero hardness for most of the purpose, or for cooling purposes and all, they recommend in the range of 60 to 70 milligrams per liter as calcium carbonate. So today we will discuss what are the different methods usually employed in water treatment plants for the removal of hardness. There are basically two different methods which is being used. They are, one is chemical precipitation and another one is ion exchange. And most commonly used one is chemical precipitation, but we have to remember that by chemical precipitation we cannot achieve zero hardness, because this is working on the precipitation principle. So we know that if some compound has to be precipitated, the soluble concentration should exceed the solubility product constant. So, the concentration corresponding to that solubility product constant will be remaining in the water. So, we cannot remove 100% or we cannot remove 100% efficiency by chemical precipitation. In chemical precipitation, what is happening? Here we are converting calcium hardness to calcium carbonate and magnesium hardness to magnesium hydroxide, because these two compounds, calcium carbonate and magnesium hydroxide, are having very low solubility and they will be precipitating out easily, and these precipitates are dense enough so we can settle them properly. And most commonly employed method of chemical precipitation is lime soda ash process. So, we will discuss about this process in detail. So, in hardness removal we have to add lime and soda ash depending upon the type of hardness present. So, we will first discuss about the reactions involved with these chemicals and the hardness present in the water. So, first what will happen, if calcium carbonate hardness is present, that means calcium is associated with anions which causes alkalinity, that means bicarbonate or carbonate. So, the reaction is like this, calcium plus 2 bicarbonate, that means calcium bicarbonate reacts with lime, calcium oxide and water to give 2 calcium carbonate and 2 water molecule. So, here the calcium carbonate is formed, this is a precipitate and it is dense enough to settle down. And now coming to magnesium carbonate hardness, because the anion is bicarbonate, magnesium bicarbonate plus calcium oxide will give calcium carbonate plus magnesium carbonate. Here calcium carbonate is easily settleable and the solubility is very less. So, we can remove that very easily, but magnesium carbonate is having high solubility. So, magnesium we cannot remove in the form of magnesium carbonate. We have to convert this magnesium carbonate into magnesium hydroxide. That is the second step of equation. Magnesium carbonate plus calcium oxide gives you calcium carbonate plus magnesium hydroxide. Both are precipitates and which can be removed easily. Now, we will see how the non-carbonate hardness are removed. So, magnesium, whether it is associated with sulphate, chloride or nitrate, okay. So, magnesium sulphate or magnesium chloride or magnesium nitrate, when it reacts with lime, we will be getting the corresponding magnesium hydroxide and calcium sulphate or calcium chloride or calcium nitrate. All these compounds are soluble in water or their solubility are very high, and magnesium hydroxide is a precipitate and which will settle down easily. And now coming to calcium non-carbonate hardness. Calcium, whether it is present in the form of sulphate, chloride or nitrate, when it reacts with sodium carbonate, that means this is soda ash, it forms calcium carbonate plus sodium sulphate or chloride or nitrate. So, these compounds are soluble and calcium carbonate is the precipitate. So, we can remove calcium carbonate hardness as well as calcium non-carbonate hardness. So, all hardness, that means calcium carbonate hardness, magnesium carbonate hardness and magnesium non-carbonate hardness, the chemical required is lime. But calcium non-carbonate hardness we have to add soda ash. So, this is the important point to be remembered here. And if the water is having dissolved carbon dioxide, that also will be consuming quite amount of lime. So, this is the reaction, carbon dioxide plus calcium oxide gives you calcium carbonate. But if the dissolved carbon dioxide concentration is more than 10 milligram per liter, it is always advisable to go for aeration so that the carbon dioxide can be expelled from the system. So, the lime consumption will be very less. Instead of lime, we can even go for caustic soda. Now, how can we find out the lime and soda ash requirement? This is a table which can be used to calculate the amount of lime and soda ash required for the treatment. If calcium carbonate hardness is present, okay, and if we express the amount in equivalents per liter or milliequivalents per liter, so say X milliequivalents of calcium carbonate hardness is present. So, we have seen the equation earlier like this, calcium carbonate hardness or 1 mole require 1 mole of lime. So, that is what here it is represented, calcium hydroxide required is X and soda ash required is 0. So, coming to magnesium carbonate hardness, if we have to remove X equivalents or milliequivalents of magnesium carbonate hardness, we have to add calcium hydroxide 2 equivalents. The reason is, first magnesium bicarbonate will be converted to magnesium carbonate, which is it is a highly soluble compound. So we have to convert this magnesium carbonate again to magnesium hydroxide. For that 1 mole of lime addition is again required. That's why here 2x is coming and Na2CO3 required is 0. Now coming to calcium non-carbonate hardness, amount removed is x. So calcium bicarbonate required is 0 and soda ash or Na2CO3 required is x equivalents per liter. And magnesium non-carbonate hardness, if you want to remove, we have to add, if we want to remove x, then we have to add 1 mole of or 1 equivalents of calcium bicarbonate or lime. So it will be converting it to corresponding calcium salt, and then afterwards that has to be precipitated out as using sodium carbonate or soda ash. So if magnesium non-carbonate hardness is present, we have to add 1 mole of lime or 1 equivalents of lime as well as 1 equivalents of soda ash. And coming to carbonic acid or carbon dioxide present in the system, if we want to remove x equivalents per liter of carbon dioxide, we have to add x equivalents per liter of lime. Similarly, instead of lime, we can go for caustic soda also or NaOH. The reactions are like this. One advantage of caustic soda is, okay, we have seen that for calcium non-carbonate hardness, we have to add sodium carbonate or soda ash. But if you add caustic soda or NaOH, sodium carbonate will be generated as a byproduct. Here we can see. So we can reduce the amount of sodium soda ash to be added to the system. So these are the reactions when we add or when we use soda, caustic soda. Carbon dioxide plus sodium hydroxide gives Na2CO3 plus H2O, and calcium bicarbonate plus gives calcium carbonate plus sodium carbonate plus water, and magnesium bicarbonate plus sodium hydroxide gives magnesium hydroxide plus soda ash plus water. Magnesium non-carbonate hardness plus soda ash gives you magnesium hydroxide plus sodium sulfate. So we can see that sodium carbonate is coming as a byproduct, so soda ash dose can be reduced. So if you have more non-carbonate hardness compared to carbonate hardness, okay, it is means if soda ash can be generated by the process itself, it is advisable to go for soda ash. But compared to calcium oxide, sodium hydroxide is costly. So we have to compare the cost involved in each process, and we have to select the best out of them. Okay. So again, if calcium carbonate hardness and non-carbonate hardness are almost equal, okay, and if you want to reduce the soda ash dose, then it is advisable to go for caustic soda or NaOH, because from the calcium carbonate hardness we will be getting enough sodium carbonate. That sodium carbonate will be used for the removal of calcium non-carbonate hardness and magnesium non-carbonate hardness. And here we can see that this calcium carbonate precipitates, the solubility diagram of calcium carbonate if you see, okay. Last class we were discussing about aluminum hydroxide. This calcium carbonate is also somewhat amphoteric in nature. So the solubility will be increasing both the sides of that optimum pH. The optimum pH of calcium carbonate precipitation is in the range of 9 to 9.5. But coming to magnesium, if you want to remove magnesium, the pH of the solution should be above 11. So that is very, very important. So if you calculate the chemical dose based upon this table, okay, this is only we are calculating the chemical required for the chemical reaction, but we have to add some chemical which is required for increasing the pH, because most of the cases the natural pH of water is in the range of 6.8 to 7.5 or so. So we have to increase the pH from this range to above 11. So that requires considerable amount of chemical dose. So whenever we calculate the chemical dose using the chemical equivalents, we have to add around 1.25 to 1.5 times the calculated chemical dose to achieve better performance. And one more thing is, whenever we calculate the chemical dose, we should be careful about the purity of the chemical compound. Here all the calculations are based upon pure compounds. We are assuming that 100% reaction is taking place, or whatever we are adding, it is available 100%. But most of the time what is happening, the commercially available chemical, those will not be 100% pure. So say sometimes it is 70% pure or 75% pure or 80% pure. So when we calculate the dose, we have to take into account that purity also into account. For example, if you have 0.80% pure compound, so if you calculate the dose as 1 kilogram, so we or 1 kilogram say, so we have to add anyway 1.25 to 1.5 kilogram to increase the pH up to 11. Then we have to multiply that quantity with 0.8, divide by 0.8 to get the actual amount, because if you add 1 kilogram, we are getting only 0.8 kilogram of actual chemical. So that also we have to take into account. Now we will talk about stabilization, because we have gone for chemical precipitation, and at the optimum pH calcium carbonate or magnesium hydroxide is getting precipitated, and we are removing that one by settling or by sedimentation, and whatever sludge is there we are removing. But the time we are giving for the reaction is not very large, and you know that the precipitation is a time dependent process, or in nature supersaturated solutions can exist. So the calcium carbonate precipitation, okay, the solution which is oversaturated, if you keep for long time, more and more precipitate will be forming. So after this lime softening, lime soda ash softening, if you allow that water to enter in the distribution system, what will happen? This calcium carbonate will be slowly settling down in the water, in the distribution system. So with respect to time, what will happen? This calcium carbonate will be forming a layer over the distribution system, and that keep on growing, and your distribution network or the pipe diameter, internal diameter will be gradually decreasing. So as a result, you will not be getting the design flow, or and there will be many other problems associated with that one. So what can we do to avoid such conditions? And one more problem associated with this precipitation is, we have seen for the removal of magnesium hydroxide or magnesium hardness, we have to increase the pH up to 11, and if you put that water with a pH of 11 into the distribution system for drinking purpose or other domestic purpose, people will not accept, because according to the standard, Bureau of Indian Standards, drinking water pH should not be more than 7.5. So we have to supply a water or maximum up to 8.2. So we have to supply a water which is having a pH within this prescribed or specified limit. So how can we achieve this condition? That means precipitation of calcium carbonate should be avoided in the distribution network, and the pH should be within the prescribed or specified limit. So for that purpose, we are going for stabilization. See, this is what is happening in hardness removal. Complete removal of hardness is not possible by lime soda process, because I told about the solubility product constant, that is nothing but the concentration of calcium ions and carbonate ions whatever is present. So as long as this product value is lower than the KSP value, these ions will be in solution. When it exceeds this KSP value, then slowly calcium carbonate will be started precipitating. So because of this constraint, if you go for lime soda ash precipitation, we cannot achieve a calcium concentration lower than 40 milligram per liter as calcium carbonate and magnesium, concentration of 10 milligram per liter as magnesium ions, or 40 milligram per liter as calcium carbonate. So this is what I was explaining till now. The precipitation, the solution is super saturated, and the precipitation is a continuous process. So that precipitation will be taking place in the distribution network. So stabilization, what is the purpose of stabilization? To make the water neither corrosive nor scale forming. Because what will happen, okay, we can make the water undersaturated by adding acid. So whatever the precipitate of calcium carbonate present in the system, okay, with respect to pH, okay, as the pH lowers, the solubility of calcium carbonate will be increasing. So we can make it undersaturated. But if the acidity of the water is too high, then what will happen? It will become corrosive. So, it will be corroding the network, distribution network, or wherever it comes in contact with any metal or other materials. So, what we usually do is, after the lime soda softening, we add some acid to make it non-corrosive or not scale forming, but acid quantity should be adjusted in such a way that it should not be corrosive. So, this is what usually happens in stabilization. The calcium carbonate present, we add some acid, say H2SO4, then you will be getting calcium bicarbonate plus sulphate. Or magnesium hydroxide, if you add sulfuric acid, what will happen? Magnesium sulphate and water will be formed. But if you add the mineral acid, okay, it is very difficult to control the pH, okay, because if one extra drop is there, the pH will be reducing drastically. So, in water treatment plants, mostly we go for stabilization using carbon dioxide. The reactions are as follows: calcium carbonate plus carbon dioxide plus water gives calcium ions plus bicarbonate. Here what is happening is, when calcium carbonate is dissolved in water, it will be forming carbonic acid. That carbonic acid is acting as the stabilizer here, and it will be solubilizing calcium carbonate present in the system. Similarly, magnesium hydroxide, when carbon dioxide is added, magnesium and bicarbonate ions are formed. Okay. So, if you use carbon dioxide for the stabilization, the process is known as recarbonation. And in practice, recarbonation can be done in two different ways. One is single stage and another one is two stage. Single stage, the carbon dioxide addition will be only once, and in two stage, what we do is, once it is added and whatever is the pH is has brought down to a particular point, and allow the calcium carbonate to precipitate again, that will be removed, and again add carbon dioxide to adjust the pH, that is two stage. So, I will show you the line sketch of this one stage and two stage recarbonation. So, this is the one. So, raw water is coming, along with the raw water we are adding lime and soda ash, and this is a flocculator plus clarifier or clariflocculator, whatever we have seen in the coagulation flocculation system. So, here lime is present and soda ash is present. It is reacting with the calcium and magnesium hardness present in the water, and it will be precipitating as calcium carbonate and magnesium hydroxide, and the sludge will be settling down in the clariflocculator, and it is removed as waste sludge. And here what we are doing is, we are adding carbon dioxide. So, carbon dioxide will be dissolving excess carbon dioxide whatever is present in the system, which is not removed completely. Then after this recarbonation, we are going for filtration again, and softened water will be available, and this filter we have to do backwashing whenever the pressure drop become more than the specified limit. Now, we will see what is a two stage recarbonation. Now, this shows how the recarbonation is done. Okay, recarbonation or stabilization can be done by adding carbon dioxide. This carbon dioxide addition can be done either making some combustion or ignition inside the water. So, you know that if any fuel is burned, the byproduct is carbon dioxide and water if complete ignition is or complete burning is taking place. So, usually what people do is make the ignition happen inside the water and allow the carbon dioxide thus created to pass through the water, so that the carbon dioxide will be mixing with that one. Another way of providing carbon dioxide is, nowadays carbon dioxide is available in pure form in cylinders. So, take these cylinders and adjust the flow rate according to the requirement and supply that one to the water and make sure proper mixing. So, this picture shows carbonation system with the ignition. So, here you can see that air is coming and the fuel gas is coming, and this is the igniter. So, here the ignition is taking place, and this is a submerged burner. So, whatever the carbon dioxide is produced because of the burning, it is coming out. Okay, this shows the direction of flow. Okay, and it is getting mixed up. Okay, this is the water inlet. So, whatever is happening, okay, it will happen in this chamber and the treated water will be going out. But nowadays this type of carbonation is not used. Most of the time we go for pure carbon dioxide, because if the ignition is taking place in the water submerged condition, not always 100% ignition will be taking place. So what will happen? Some amount of unburned fuel will be entering in the water and water quality will be deteriorated. So it is always advisable to go for pure carbon dioxide cylinders for recarbonation. So this is the example of a two-stage recarbonation unit. So here what is happening? Raw water is coming and lime and soda ash is added here, and this is the clariflocculator. Waste sludge is going out, and here first stage recarbonation is taking place, and again clariflocculator, the waste sludge is removing, and second stage recarbonation, filtration. So two-stage recarbonation is always advisable if you have dealing with a large quantity of water. Here we can reduce the quantity of carbon dioxide to be added and we will have better control over the system. And chemical requirement, we have already seen that how can we find out the chemical requirement for softening? By finding out the equivalent weights and the chemical reactions. How much equivalents of hardness will be reacting with the how much equivalents of chemical. From that one we can find out the chemical requirement. So here till now we were discussing about lime soda precipitation, where entire water is subjected to the treatment, and after treatment we have seen that the water will be having a very high pH. That means excess lime will be present in the water, because for calcium carbonate removal the pH requirement is 9 to 9.5, but if you want to remove magnesium the pH has to be increased to 11. So much of excess lime will be present in the system, and if you want to put the water into the distribution system, we have to reduce the pH considerably, okay, to suit the drinking water standards. So we are wasting so much of chemical unnecessarily. So if you want to optimize the chemical use, okay, we can go for split treatment. Split treatment means the water is only a portion of that water is treated and a portion will be coming without treatment, and after the treatment what will happen? Both the water will be getting mixed up. So as a result what will happen? The excess lime present in the treated water, that means which is having a pH of 11 or higher, okay, that lime will be used for the precipitation of the carbonate hardness present in the bypass water. So this split treatment, the design is based upon the magnesium hardness, because after calcium and magnesium hardness removal by lime soda softening, we have seen that around 10 to 13 milligram per liter of calcium carbonate, calcium will be present in the form of calcium carbonate, and magnesium concentration left as magnesium hydroxide in the system will be around 40 milligram per liter if expressed in terms of calcium carbonate, or it will be around 10 milligram per liter if we express it in terms of magnesium ions. And it is observed that if the magnesium concentration is more than 10 milligram per liter as magnesium ions or 40 milligram per liter as calcium carbonate, then magnesium fouling can take place in the boilers or other utensils which is used in the domestic purpose. So whenever we go for the hardness removal, we have to keep in mind that the magnesium concentration should not exceed that limit, but the problem associated with calcium is not so significant. So the split treatment is basically based upon the minimum magnesium concentration or the maximum magnesium concentration that can be allowed in the distribution system or water supply system. So this is the picture which shows a split treatment. So here what is happening is only a portion of the water is coming for the treatment. So this is the bypass flow QX, it is coming here, and lime and soda ash is added here, it is getting mixed, and the treated water is going out and carbon dioxide is added, and after that one it is here the bypass water is coming, and again we are removing some sludge and carbon dioxide addition is taking place. I will explain once again. Okay. Here the influent, what the amount, okay, here Qx is bypassed, so 1 minus Q minus Qx will be coming for the treatment. So here we are adding lime and soda ash and mixing is there, rapid mixing, slow mixing and settling. So some sludge is going out and this is the bypass flow that is coming and joining here along with the treated flow. And this is another unit. Here again we are allowing the precipitation, because what is happening here, since magnesium removal is also taking place, the pH of the water will be in the range of 11. So that is having excess lime. So this bypass water which is having a pH of around 7 to 7.5 will be coming here. So this excess lime whatever is present, that will be reacting with the calcium carbonate hardness whatever is present in this bypass water. So it will be precipitating as calcium carbonate. So we have to remove the sludge. So that's why we are giving a precipitation or settling unit here, and whatever is the water coming out, okay, it is a mixed one, treated plus untreated. So we have to go for carbonation to stabilize the water depending upon the pH. So if you want to show the line diagram, okay, this explains very clearly what is happening in split treatment. So raw water, and I told you this hardness removal or softening is required most of the time for groundwater, and groundwater we have to go for aeration because it will be having iron and manganese in the reduced form. So we have to oxidize it and remove it from the system, and moreover it may be having dissolved gases which causes bad odors, and moreover if carbon dioxide is present in excess, by aeration we can remove that one, so that we can reduce the lime dose required for this softening operation. So after aeration what is happening, the water is coming here, we are adding lime and soda ash here, and what after the chemical addition it is going for a rapid mix. Here the chemical is thoroughly getting mixed with the water coming, and then slow mix. Okay, slow mix is for the flocculation, so that after the chemical addition the flocks will be formed. That flocks has to be agglomerated to get bigger flocks, then only the settling will be effective. And after the flocculation then we have to go for settling, and after settling what is happening, this is the split portion of the flow that is coming and entering here. Okay. So it is advisable to provide another settling unit here, or you can directly go for recarbonation then filtration. So now we will see how to find out the quantity of water which we have to treat and which we can bypass. Okay. It is all depending upon the magnesium concentration what that is present in the raw water, and what is the magnesium concentration you need after the treatment and the mixing. So we have to take a mass balance based upon magnesium, because we are assuming that the calcium hardness whatever is there, it is not going to create much problem in the domestic uses. So here what is happening, Q is coming, Q is the flow rate, 1 minus x is 1 minus x into Q is going for the treatment, and X portion is coming without treatment, or it is a bypass portion, and mgr, this is the magnesium concentration in the raw water, and mgt is the magnesium concentration in the treated water, and mge is the magnesium concentration of the treated water plus the untreated water together. So remember again, mgr is the raw water magnesium concentration, mgt the treated water magnesium concentration, and mge is the mixed water magnesium concentration, and x is the bypass quantity, and 1 by x into q is the treated quantity. So how can we take the mass balance of magnesium in the entire system? Q into mge. Okay, this is the total magnesium concentration coming out. See, Q into mge. So that is equal to Q into 1 minus x into mgr. Okay, so this is the magnesium concentration whatever is entering in the system of treatment, and we will see what is getting removed here. Q into 1 minus x into mgr minus mgt, that much is getting removed from the system. So the sum of this one will be the thing coming out after the treatment, and Q into X into mgr. This is the magnesium concentration in the bypass stream. See here, mgr is coming, Q into X is coming, so that is the total magnesium concentration coming. So if you take a, if you cancel the common terms, then we will be getting this form, mge is equal to X into mgr plus 1 minus X into mgt, because 1 minus X is the treated thing and the concentration of treated water magnesium is mgt. So 1 minus X into mgt plus X into mgr, that gives you mge. So if you want to find out mgt, mgt is nothing but mge minus mgr into X by 1 minus X. Okay. Mgt is treated water magnesium concentration. So if you want to find out the X value, what we have to do? Okay, we are assuming that mgt is equal to 0. That is the condition where we can get what is the maximum quantity we can bypass. We know that magnesium concentration cannot be made 0 by precipitation, but for easiness we are assuming that magnesium concentration in the treated water is 0. So we will get an X max is equal to mge minus mgr. That means whatever is the required magnesium concentration in the blended water by what is the raw water magnesium concentration, that will tell you what is the amount of water that can be bypassed. So again, the bypass quantity is a function of what is allowable magnesium concentration in the blended or final water by the raw water quantity. So if the raw water magnesium concentration is very high, then this X max, okay, the fraction bypass will be low, okay, and vice versa. Now we will see how to solve a problem in this softening. This is the problem. The following raw water analysis has been provided, and TDS is around 746 milligram per liter, calcium 140 milligram per liter, magnesium 44 milligram per liter, sodium 28, potassium 4, bicarbonate 374 milligram per liter, and sulfate 236 milligram per liter, chloride 34, pH 7.5. So we know that when we talk about a water, it is electrically neutral, so the total amount of anions should be equal to the total amount of cations. Okay. So what we have to do here is, we have to determine the lime and soda ash dose required to soften this water. So we know the constituents, we have to do the softening, or we have to find out what is the amount of chemical required for the softening process. So now we will see how to solve this problem. The first step is compute the carbonic acid concentration of the water, because carbonic acid also will be consuming a portion of lime whatever we are adding to the water. So how can we find out this one? So for computing the carbonic acid concentration, what we have to do, we have to first convert bicarbonate concentration into moles per liter, then to equivalents per liter. So if you want to convert the concentration to moles per liter, what we have to do, we have to divide the weight in grams with the molecular weight. So that's what I have done here. Concentration in milligrams per liter divided by 1000, you will be getting the concentration in grams per liter, and that divided by the molecular weight, you will be getting moles per liter. So 374 milligrams per liter of bicarbonate is equivalent to 6.12 into 10 raised to minus 3 moles per liter. This 61 is the molecular weight of bicarbonate. Now we can calculate what is the total carbonic acid species concentration using this equation. Ct is equal to bicarbonate concentration by alpha 1, and we can calculate alpha 1 at a particular pH, and I have not discussed about this one in this lecture. Okay. So you just remember that there is a formula to find out the total carbonic acid species, and by using that one we can get the Ct is equal to 6.58 into 10 raised to minus 3 moles per liter. Now if you know the total carbonic acid species concentration, we can calculate what is the carbonic acid concentration, that is equal to bicarbonate minus carbonate. So at a pH of 7.5, the carbonate term may be neglected, this term, because you know that the concentration of bicarbonate, carbonate etc. are pH dependent. So at high concentration there will, at a pH of 7.5 there will not be any carbonate, everything will be in the form of bicarbonate. So the carbonic acid concentration is equal to Ct minus bicarbonate concentration. So you will be getting a value of 0.46 into 10 raised to minus 3 because this is the total Ct and this is the bicarbonate concentration. Now we convert this carbonic acid concentration into milligrams per liter. What we have to do, multiply it with the molecular weight, then we will be getting in terms of milligrams per liter. So H2CO3 present in the system at a pH of 7.5 is only 28.6 milligrams per liter. Now the next step is, what we have to do is, we have to construct an equivalence table for chemical species of interest, because we have seen that all the compounds we got the concentration in terms of milligrams per liter. But if you want to find out the chemical dose, we have to convert them into equivalents per liter. That is what I have done here. So we know the molecular weight of each and every species. So and we know the weight. Then if you want to find out moles per liter, what we have to do? The concentration in grams per liter divided by the molecular weight. Then you will be getting in terms of moles per liter, and multiply the moles per liter by the number of equivalents in a mole, then we will be getting equivalents per liter. So that is what I have done here. So calcium 140 milligrams per liter is equivalent to 3.5 into 10 raised to minus 3 moles per liter, or that is equal to 7 into 10 raised to minus 3. Similarly, I have calculated for each and every species and reported here. And the third step is construct an equivalence diagram for the cationic and anionic chemical species. When constructing this diagram, the calcium equivalents should be placed first on the cationic scale, and immediately following calcium, the magnesium equivalents should be shown. Okay. Once again I will explain. Construct an equivalence diagram for the cationic and anionic chemical species. When constructing this diagram, the calcium equivalents should be placed first on the cationic scale, and immediately following calcium, the magnesium equivalents should be shown. So that is what I have given here. And what about the anions? The bicarbonate equivalent should be placed first on the anionic scale, and immediately following bicarbonate should be the divalent species, which would be in turn be followed by other monovalent species. So this is the equivalence diagram for cations. So first we are placing calcium. So we have seen that calcium is 7 milliequivalents, and then comes magnesium. So 10.64 is the total of calcium and magnesium, and then comes sodium. So we are following the order whatever is specified. So calcium is 7 and magnesium is 3.64. So sum of calcium and magnesium is coming 10.64, then sodium. Similarly, anions, first we have to put bicarbonate, then sulfate, then monovalent anions. So bicarbonate is coming as 6.12 milliequivalents. Then the sum of bicarbonate plus sulfate will give you 11.04 milliequivalents per liter. Then it is coming 12. And we know that the total cationic species concentration should be equal to total anionic species concentration. And what is the requirement of this equivalence diagram? Because with the help of this equivalence diagram, we can find out what is the calcium carbonate hardness, calcium non-carbonate hardness, magnesium carbonate hardness, and magnesium non-carbonate hardness. So that purpose we use this equivalence diagram. So from the equivalence diagram, that is what I have done here. The calcium carbonate hardness is equivalent to 6.12 into 10 raised to minus 3, because it is corresponding to this bicarbonate concentration. Then magnesium carbonate hardness is 0, calcium non-carbonate is 0.88, this is coming from 7 minus 6.12, and magnesium non-carbonate hardness is 3.64. Now based on the chemical requirement indicated by the softening reactions, we have to compute the lime and soda ash dose. So we know that if 1 equivalents per liter of calcium carbonate hardness is present, we have to add 1 equivalents of lime, calcium hydroxide. So that is what is written here. And for magnesium carbonate hardness, it is already 0, and if it was there, we have to add 2 equivalents. And calcium non-carbonate hardness, we have to add Na2CO3, the same equivalents, and magnesium non-carbonate hardness, we have to add lime as well as soda ash, and carbonic acid we have to add only lime. So the total chemical requirement is coming 10.62 into 10 raised to minus 3 as calcium hydroxide, and 4.52 into 10 raised to minus 3 as Na2CO3. So the last step is convert the lime and soda ash requirement from equivalents per liters to milligrams per liter. So how can we do this one? So what we have to do, we have the equivalents per liter, then you have to convert it into moles per equivalents into grams per mole into milligrams per gram. Okay, so we will be getting in terms of milligrams per liter. So 10.62 into 10 raised to minus 3 into 0.5, because 1 mole is having 2 equivalents, that is why this 0.5 is coming, and this is the molecular weight, and this is for converting grams to milligrams. So you will be getting the calcium hydroxide requirement as 392.94 milligrams per liter as calcium hydroxide, and soda ash requirement is 240 milligrams per liter. So till now we were discussing about the hardness removal using lime and soda ash process, but we have also seen that we can go for hardness removal using ion exchange, and this process is commonly used in industry. So here what we use is ion exchange resin. Resins are used. So in the resins, what is happening, they will be having some matrix, on that one specific functional groups are attached. Mostly it is H plus ions or Na plus ions, and hardness removal resins we usually use sodium exchange resins, and sometimes we can even go for naturally available ion exchanges also. For example, natural zeolite, that is sodium aluminosilicate. Sodium aluminosilicate is naturally available material. It is known as zeolite or green sand. Okay, that is also having very high hardness removal capacity. So in ion exchange process, what is happening? So one ion will be going, which is having more affinity to the functional group. It will be going and sitting there, and it will be replacing the other ion present there. So an equal amount of ion will be going and coming. So in ion exchange process, if you take the total solution, what will happen? The total dissolved solids concentration, if you express in equivalents per liter, it will not be changing. Only specific ions will be getting transferred and other ions will be coming into picture. So I will show you how this is happening. So we have some matrix. So this is a functional group. Okay, different functional groups are there. So these functional groups are having high, okay, so cation exchange resins. Okay, this functional group will be having high affinity to cations. So we will be having initial the resin in the form of RNA or RH form. Okay, that means both are cations, Na plus or H plus. So what will happen? Okay, this R will be having high affinity to calcium and magnesium compared to this sodium. So when we put this resin, okay, this is the resin matrix. This is the resin matrix. So when we put the resin to a hard water, okay, this is the water, hard water, which is having lot of calcium ions and magnesium ions. So what is happening? Okay, we have many resins. So this resin, Na plus ion, Na plus will be coming to the solution, and calcium ion or magnesium ion, whatever is present in the water, it will be going to the resin. So we can see the resin should be electrically neutral, so as the water should be electrically neutral. So this sodium ion is having plus 1 charge and calcium ion is having plus 2 charge. So what will happen? For each calcium 2 plus ion which is going to the resin, okay, 2 Na plus ions will be coming out. Okay, this is the basic principle of ion exchange. And why this calcium and magnesium is getting absorbed more? Because calcium and magnesium are having very high affinity compared to sodium. If you want to write the chemical equation for this one, we can write like this. calcium or magnesium plus anion. Anion is the functional group present in the resin plus this is means calcium and magnesium and this anion, that is the one what is present in the water, because calcium may be in the form of calcium sulfate or calcium nitrate or calcium chloride or calcium bicarbonate. Okay. So, this anion is whatever is the one which forms the other part of this metal salt, and that will compare with NaR. R is the functional group of the resin. So, you will be getting calcium and magnesium combined with R plus 2 Na plus anion, because calcium and magnesium are divalent ions. So, naturally 2 Na ions will be coming out. So, after some time what will happen, your ion exchange resin, the capacity will be exceeding or capacity will be exhausting. So, it will not be able to take any more calcium and magnesium ions. So, we have to regenerate the ion exchange resin. So, in the regeneration what will happen? So, we have already seen that this calcium and magnesium is having high affinity to the resin. So, if you want to reverse the reaction, how can we do it? By adding high concentration of sodium ions. If you add very high concentration of sodium ion, this reaction can be reversed. So, we can see the regeneration. Regeneration is like this. We have already calcium and magnesium in the resin. So, we are adding very high concentration of NaCl. And the concentration should be very high, otherwise this reaction will not be possible. Then you will be getting calcium and magnesium along with 2Cl. The Cl is coming from the sodium chloride, and you will be getting 2 NaR, whatever was there initially, this one. So, the regeneration will be taking place and the resin will be regenerated. So, we can use that one. But here you see the amount of sodium chloride used for the regeneration is very high. We have to go for a very high concentration of sodium chloride solution, and the factors affecting the exchange are, first one is the solid medium on which the functional group is attached. Second one is exchange material. Okay, third one is quality of regeneration. Material, and fourth one is overall quality of water. Overall quality of water. So, this is very important. So, if you are going to use ion exchange method for the hardness removal, what we have to do? We have to go for sedimentation, coagulation, flocculation, then filtration. Afterwards only we can go for this ion exchange. Otherwise what will happen? Whatever the calcium carbonate or magnesium hydroxide precipitation taking place, or whatever is the flux remaining after coagulation, flocculation, that will be coming and depositing on the ion exchange resin, and it will be clogging the resin and reducing the efficiency. And if you are using this ion exchange for groundwaters, if iron and manganese are present, because the water is coming in contact with air, iron and manganese will be getting oxidized and their precipitate also will be formed. And that in that case also, what we have to do? We have to go for aeration, then filtration, then go for ion exchange. And most of the ion exchange resins, whatever is used for this hardness removal, is having a capacity of 15 to 100 kilograms per meter cube. Okay, 15 to 100 kilogram per meter cube. That means it can remove around 15 to 100 kilogram of calcium or magnesium ions. And the sodium chloride requirement is around 80 to 160 kilogram NaCl per meter cube, and we have to provide that one in the form of 5 to 20% solution. The solution should be having high concentration, that means 5 to 20%, that means 5 grams per 100 ml or 20 grams per 100 ml. The concentration should be in this range, and the velocity or the flow rate with which it has to pass through the ion exchange resin is also specified, that is 40 liters per meter square per minute. Okay. If you pass it at a high velocity, the exchange will not be taking place properly. So, we have to provide a flow rate in this range. Okay. If the flow rate is high, the efficiency will not be high. Okay. So, usually the ion exchangers are provided in closed chambers, something like this. Okay. It can be either upflow mode or downflow mode. Okay. Here the ion exchangers are here. So, water can be distributed equally from here. Okay. And it will pass through the ion exchange resin, and we can collect here the treated water, or this way also it is possible. So, this will be having more efficiency because it will have more contact with the ion exchange resin, because short circuiting can be avoided if you go for upflow mode. Then the regeneration, we can either go in the upflow mode or in the downflow mode, but you imagine around 60 to 150 kilogram of sodium chloride per meter cube of the ion exchange resin. So, that much of sodium chloride is coming along with calcium and magnesium ions. So, the regenerant whatever is coming from the ion exchange resin, it is having very high TDS. So, we cannot just discharge that one, we have to have proper provision for collecting them and keeping them or treating them and disposing them. So, that is an important point to be remembered when we go for ion exchange. The regenerant whatever is happening, that is another form of pollution. So, we have to control that one, because if you discharge it into surface water, the salinity will be increasing too much. And another advantage of this ion exchange process is we can remove hardness 100%. 100% removal of hardness is possible. So, most of the time what we do, or most of the time what industries do is no need of removing the hardness 100%. So, here also we can go for split treatment. That means a portion of the water is allowed to pass through the ion exchange resin, and the remaining portion is bypass the ion exchange resin, and finally what will happen, blend the water which is treated with the untreated water. So, you can maintain a calcium and magnesium concentration within 50 to 60 milligram per liter, which is permissible for drinking purpose and industrial purpose. So, this is very important. Okay. So, depending upon the quality of water requirement, we can decide which type of treatment you have to go and how much water we need to treat. So, we will summarize today's class. So, we have seen what is hard water, what is soft water, and what is the treatment we can go for to remove the hardness. So, we have seen that the most commonly used methods are ion exchange and chemical precipitation, and most of the time we go for chemical precipitation because that is less costly. And in chemical precipitation we use lime and soda ash as the chemical. Instead of lime, we can even go for sodium hydroxide or caustic soda, depending upon the type of the hardness and quantity of hardness present. Then in lime soda process itself, we can go for split treatment. That means we need not treat entire water, and after that go for recombination. So, in split treatment, whatever the excess lime we are adding for pH adjustments, we can take care by adding the raw water. So, whatever the water treated after lime and soda ash process, we have to stabilize it before putting it into distribution system, because that will be having high precipitation potential and the pH will be high. So, we have to reduce both the things. For that we have to add either a mineral acid or carbon dioxide. In water treatment usually we go for carbon dioxide addition. So, that is known as recarbonation or stabilization. And this recarbonation itself we can do in two different ways, single stage or double stage. The major purpose of this stabilization is make the water non-corrosive or non-scale forming. If the water is scale forming in nature, what will happen? The distribution system diameter will be getting reduced with respect to time. If it is corrosive, what will happen? The water will be eating away the distribution system.